Thanks, Fernando, for that lovely introduction. Is the mic good? Can people hear? Can you hear me in the back? All right, great. So welcome, thanks for coming. Like I said, I want to talk about NumPy, and probably many of you are familiar with NumPy, but my experience is a lot of people use NumPy, but it's sort of this thing that comes in a box from Amazon, and you open it, and there it is. You don't really know sort of where it came from, what's going on. So I want to talk a little bit about sort of, if you open, peek behind the scenes, how that works. So this is not, I'm not going to like start walking through all the NumPy code base. There will be some technical material, but it's also about sort of the social structure and the planning and that kind of stuff. So, right, so without further ado, I mean, just to make sure we're all on the same page, like I said, probably you all know a little bit about what NumPy is, but so what NumPy does, it gives you fast and friendly array types in Python. So things like you have an array can provides sort of these powerful indexing capabilities, vectorized operations. So this looks like a simple bit of arithmetic, but if those are NumPy arrays, that they could be 4-dimensional giant piles of numbers, and it will line them up and do all those operations on all of the elements. So a lot of computation expressed very compactly. Important things like linear algebra, so this is, that @ sign is Python's matrix multiplication operator, so that's one way to solve an ordinary least squares problem. And importantly, NumPy is sort of, like Fernando said, the standard that all these other packages in the Python ecosystem use. So this is why pandas and matplotlib can talk to each other, is because they both have the sort of common representation that NumPy provides. Another sort of funny thing about NumPy compared to a lot of sort of its competitors, if you will, is that it's not something that's built into Python itself. It's an ordinary library, if you will, which is not historically how we've tended to do things in science, right? So there's languages that are written for scientific numerical use and have sort of specialized stuff for that, but maybe are not so great for more general purpose use. Or you have sort of the general purpose languages coming out of sort of computer science departments in industry that are not so useful for, or more awkward for scientific use. And NumPy is in sort of this funny thing where it's taking this general purpose language, Python, that's just really popular for teaching kids and running websites and powering Instagram and just all this kind of stuff, and turning it into one of these numerical languages. It's not the first such library to do that, but it's the first that sort of reached this level of popularity that sort of really started to give those languages a run for their money. And that sort of puts it in a unique place where we don't necessarily, we're sort of doing something different than a lot of what's come before. It also, because it's not baked into language, is something that can evolve on its own timescale. And so one benefit of that is that it's a very, very mature library. So the history here is quite complicated. It goes all the way back to '94. Jim Fulton started experimenting with matrices in Python. James Huguenin took that and built the numeric package around it. The little ... there is hiding dozens of people with major contributions, but I tried to highlight some of the major names here. There was sort of the split where the Space Telescope Science Institute had some issues with numerics, started their own thing. Travis Oliphant then sort of reconciled the two back in 2005, and now here we are 12 years later. And now, one benefit is that there's been a lot of evolution, a lot of hard-won lessons over that 23-year history. A downside is that this is actually a single code base that's changed name several times all the way through that time period. So that's 23 years of crufty C code, and some things have been cleaned up, things have changed, but there are also strange things have accumulated along the way. But to just sort of give you a sense of how it's put together at a high level. And this is actually something I think is really a great feature that's sort of one of those hard-won pieces of knowledge, is that so NumPy is divided into 3 parts. So there's the containers, is the actual array object. And that has this sort of flexible way of representing arrays in memory. And it's nice in various ways. I won't go into all the little details. But what's interesting about it is that the array object itself doesn't know anything about numbers or booleans or the kinds of things you actually put in an array. It just knows how to work with chunks of memory. Then you have the dtype objects, which know things like, oh, okay, I have an 8-byte float that's little endian, and it knows how to how to store that in memory, how to convert it to and from a Python object, but it doesn't know about how to do like array indexing or anything like that. So the array object and the dtype work together to give you an actual useful array, and it's a sort of a powerful kind of decoupling because it means you could add, have lots of different types of data, for example. And then finally, there's the actual operations on arrays. So like ufuncs, like these are like these vectorized operations. You take the logarithm of an array, and it goes and loops over all the different pieces of the array and takes the logarithm of each of them, puts it back together. And this also provides sort of powerful generic tools like broadcasting is NumPy's name for the way if you have multiple, like you're adding two arrays together and they don't have exactly the same shape, how it kind of rearranges them to make them fit. So like the most simple case is if you have like a vector and then you type like +1, and then well, okay, you can't, what does that mean? These are different shapes. Well, it takes that one and it makes a whole vector full of ones, and then it adds those together sort of automatically. But it's also a more general tool than that. This is something that actually MATLAB has now stolen from NumPy. The influence is going back the other way now. So there's a lot of wonderful stuff here. And it's been incredibly successful. So just to kind of give you kind of a sense of the order of magnitude here, one way it's distributed, I don't even know if it's the most popular way people get NumPy, but the one I have easiest statistics for is the Python package index, where it's currently about 2.5 million downloads per month. Or if you look at GitHub, there's more than 5 million files people have put on GitHub in which they're using NumPy. As far as I can tell, that's more than any other Python package. And there's, like Stack Overflow had a blog post last month where they said, well, we found that in high-income countries, Python, they have this curve of like people like, it's one way to like find out how people understand language. Are they asking questions about it? Are they looking at question pages about it? And the Python curve just goes like this, to the point where it's now the most popular language at least in high-income countries, and is getting there in the rest of the countries. And they said, why is that happening? And as far as I can tell, it's because of stuff around NumPy and the ecosystem around it, right? So it's tremendously popular, influential. And somewhat remarkably, it's done all this basically without funding. There's been a few times over its history where like a company has said, oh, you can work on this on your work time for a few months or things like that. But for the most part, this is just all people doing stuff in their nights and weekends. A rather pretty small group of people. So that's kind of remarkable, right? So the picture I'm trying to paint here is sort of one that's both, there's a lot of opportunities here and a lot of challenges, right? So on the one hand, we have this wonderful foundation that's sort of been evolved over many years. We also have 23 years of accumulated cruft. We have this huge user base, which means that there's a lot of opportunity to have powerful impact here, right? If you improve NumPy, the new release, millions of people benefit from that. But it's also then you try and clean up some cruft and you discover that, people start screaming at you because it turns out they were using that. I mean, here's my favorite example of this. Let's see if I remember this right. Is a year or two ago, someone refactored how the median operation NumPy works. So the median is, right, you pick the middle element of an array. But if there's an even number of elements, right, there isn't just one that's in the middle, there's two. So the standard thing is you take the two and then you take their average, right? And it turned out that it used to be that if there were an odd number of elements, we'd take the middle one and then we'd take the average of it with itself. Like it was just how the code was written. It always took the average. Of course, that doesn't do anything, right? It's just the average of something with itself is just the same thing. And when it got refactored, that got removed. And then we made the release, and then immediately someone started yelling like, oh no, you broke my code, because you're no longer taking the average of the number with itself before returning it. Can you put that back, please? And there actually is a good reason for why they need it. I mean, but right, like at that level, like, would you have expected that? No, no, we had no idea, right? Like this stuff, this is kind of the environment we're working in, right? And we have this robust contributor community. Yeah, what? Okay, it has to do with if you want. We'll actually get into this more later in the talk, but the question is, what was the reason? And it has to do with if you want to like make objects that are not quite real NumPy arrays, like you subclass ND array and then add some new features, then there's certain operations you can hook and some you can't. And it turns out median you can't, but average you can. And so they were relying on that to get some special behavior. in the media. Yeah, and it's kind of a mess. The subclassing is its own whole mess. That one of the things we'll be talking about later is how we're trying to like come up with a better alternative. But yeah. Okay. Anyway, where was I? Right. Robust contributor community, but it's sort of nights and weekends, people with strong opinions, limited time. It can be hard to sort of move things forward in that kind of environment, especially sort of larger changes. And even 5-10 years ago, the big problem in our world was like we're chasing the taillights of other more mature packages like MATLAB or whatever. Just how can we get more stuff into Python so we can use it? At this point, I mean, it's not in every way, but in many ways, we've caught up or even surpassed these leading things. So now, that's wonderful, but where do you go next? It's not immediately obvious, right? So, like I said, a lot of opportunities, also a lot of challenges that are kind of facing off. And one thing you might think is that, well, so like I said, we've done all this with just this small sort of group of volunteers. Couldn't we do amazing things if we had more resources? What if you took money and brought that in? Like, all kinds of things might happen. Now, this is sort of there's sort of a joke here, like there's sort of an ambiguity there. So one possibility is that an explosion of wonderful things occurs. But there's also another kind of explosion you can have, right? So we've sort of done things one way. If you start throwing a lot of resources, you might break what you already have. And this is not a hypothetical concern. This isn't like a hypothetical worry. Because one more thing about NumPy is that it is now funded. Thanks to the Moore Foundation and hopefully another mystery partner to be announced soon, BIDS has a grant to work on improving NumPy. We have a team here where there's sort of going to be me and others, some you'll see around the room, who are going to be helping sort of make this work. And it's also, since this is sort of BID's general institutional mission is to try and make these kind of things happen in general, improve the open source scientific software ecosystem. A sort of secondary goal of having this team structure and all that is we want to try and figure out sort of how do you do this kind of, can we replicate this kind of thing in general for other projects? Can we sort of build some institutional knowledge about how to get a grant for a project and make it more awesome? But concretely, what this means is that sometime in a few months from now, we expect to have 3 or 4 full-time people at BIDS working on NumPy. Our job ad is currently in HR review. We will see when they get it back to us. But that's kind of where we are. And so obviously, we want to make sure that we get the nice, wonderful outcome. How are we going to do that? So let me talk a little bit about sort of how we're planning to approach this. So the first thing is that even though we'll have a lot of resources here, and this could be a problem. So you couldn't see the little print on that GitHub screenshot, but it showed 90 commits over the last 30 days there. So it's like 3 commits a day. And we're talking about 3 or 4 full-time people, probably going to do more than 1 commit a day. Right? That's like larger than the entire rest of the community. So there's some concern about sort of maintaining that balance. And so one thing we want to sort of be very clear up front is that while we're going to have a lot of resources here, it's still the community that's in charge. We're trying to help make that happen, make what the community wants happen. So both at a very high level, like everything else I'm going to be talking about in this talk comes out of this dev meeting that we held 2 years ago. Thanks to BIDS and SciPy for helping sort of sponsor that, pay for travel and things like that. So these are all ideas that sort of came out of these community discussions. But also sort of more concretely, NumPy now has a formal governance structure, which makes clear that any app maintainers have veto power, basically, which is doesn't mean we think that people are going to be constantly obstructing progress by vetoing everything. But the point is to make sure that if someone, we have to make them happy rather than the other way around. Even though we may have the money, it's the important thing is to make the community happy, and that sort of this is to keep us honest, right? We're not going to ask for any special privileges for our hires. Like they'll show up, they'll have a lot of time to spend, so hopefully they probably will become maintainers and get some stature in the community that way. But it's not automatic just because we hire them, they get any special privileges. And one of the things we want to actually do with this time that people have to contribute is to help act as a force multiplier on that community. So things like make it easier for people to get started, improve our documentation for developers, take on some of the review load, migrate code from C to Cython. So I don't know if people are all familiar with Cython. one of the problems in NumPy is it's mostly written in C, and then there's the Python part, and you kind of have this awkward interface between them often. And Cython is this like mutant perversion of nature, half Python, half C language that's really nice for sort of straddling that boundary. And so, I mean, not all of NumPy is best in Cython, but there are parts where that would make it a lot more approachable and easy to work on, and generally sort of clearing out cruft. Now, of course, that's not the limit of our ambitions. We didn't go out and get a grant just for that. We also have some larger changes we're hoping to make. But before we get into that, there's some sort of meta question about like how do you even go about making big changes to a project like NumPy. There's two big kind of approaches. One is like, we're gonna change everything. It's gonna be amazing. We're gonna do it all at once, and that, just clear out the old, in with the new. The other approach is sort of the more incremental. We'll make multiple changes in place, and it's the latter is the one that we're going to go for here. We sort of call it the rebuilding the airplane in flight, which is it makes intentionally kind of funny, right? I mean, it's pointing out that this is challenging, right? It's a lot of work to try and it's like, okay, the airplane's flying, all right, and now we're going to take that wing off. But so we got to first, build a second wing next to it, and then take it down, and then build a new wing there. I mean, like, there's a lot of sort of extra work to do that, but there's also a lot of advantages. Or I guess here's another analogy that is sort of how I think about it. Let's talk about earthquakes. We're in California. It's on topic, right? The way earthquakes work is that you've got two plates sort of pushing each other, and there's these conflicting forces. There's tremendous forces trying to move the Earth, right? And there's also tremendous forces holding it still, because it's trillions of tons of dirt, right? And so there's kind of two things that can happen, right? It will move eventually, but the one possibility, what you hope, is that it kind of makes lots of little motions, right? And that's how things usually are around here. So this is the earthquake map I pulled up last night. You can see like there's just like that's just in 12 hours a pile of earthquakes all over California, and that's great. It's wonderful. We love this because lots of little earthquakes let it release that energy without catastrophic destruction. The other possibility is if it's stuck and it doesn't move and it doesn't move and it doesn't move, then eventually it makes a big jump and releases all that energy all at once, and that's a catastrophic earthquake. Now, so NumPy is kind of in a similar position, right? It's down at the base of the stack, and there's this tremendous pressure on it, both to keep moving forward, because millions of people want new features, and we want to keep making scientific Python more and more wonderful. But there's also this tremendous pressure, don't touch anything, because you will break stuff, right? You'll remove that meaningless average that turned out to be critical to, I think it was AstroPy, right? And so there's these conflicting forces, right? And our options, realistically, there is no option which is never break anything. Because the only way to do that is say, okay, we're just not touching anything, even bug fixing, we're just keep everything the same, NumPy is done. And that might work okay for a year, 2, 3 years, but eventually people get sort of fed up. They're like, we want new features, they want new stuff. And what they'll do is eventually some competitor will spring up that will do things the new, better way. And then what happens is that eventually we have to have this very painful transition for a whole community, like Python 2 to Python 3 or something, where everyone has to stop what they're doing, rewrite everything all at once to get to the new thing. And that's like the big earthquake that we want to avoid. So to avoid that, so this is kind of the approach we're taking. This is right, so we're not doing the big rewrite. We're trying to do incremental change. And this means we have to sort of accept that we are going to break things. That's just a fact of life. So we want to do that sort of in the most sort of mindful, careful way we can, and bring the community with us as we're making these changes. Instead of having to have a big bang, everyone off the plane, you get on the new plane, kind of one moment when everything breaks. And to try and do that in sort of in a sensible way, again, there are particular strategies you can use. Like we improve our testing to catch when we're breaking things early instead of waiting for the release. We can have better like documentation when something's going to break. Make sure people know that. Make sure it's clear why it's going to happen, what they need to do to change it. We could do a better job there. And so on. We can get into more of these details if people are interested, but you get the sense, you get the idea. All right, so after all that throat clearing, what are the big features that, the big exciting things we're talking about doing with, spending this breakage budget on enabling? So the first one is extensible dtype system. Doesn't that sound exciting? So here's what I mean by that. So like I mentioned, dtypes are this part that talks about like that's how you have floats or integers or booleans in an array. But there's actually lots of other things people would like to put in their arrays. They want to have sort of floats that have sort of this more sophisticated, or integers also that have more sophisticated tracking of like, it's a number or it's missing. It's kind of important for statistical purpose. This is a major feature of R that we don't have right now. Things like numbers with units attached, so that if you try to add an array of meters and an array of seconds, you get an error instead of just silently getting nonsense. Holding categorical data, similar to what R does with its factors. NumPy has some string support, but it's kind of grotty and hard and annoying and limited. We'd like to do better. Date times are this huge, complicated issue. And it turns out even like the way astronomers think about time is very different than the way like finance people think about time. And so on, right? So now we're not saying we're going to go implement all these features. Like some of that stuff may eventually end up into NumPy, but that's not the initial goal. The first goal is to make it so that you can go implement these features, right? So right now it's, conceptually the dtypes are sort of factored out. It's the self-contained thing. It provides a certain interface to the rest of the system. But in practice, it's not really possible. There's some weird, annoying limitations that make it both awkward or impossible to implement many of those features. Like the architecture's there, but not the details don't work. But what we want to do is to make it possible. So if you say, OK, I want to define a categorical type, you say, all right, here's my class. It's a dtype. I need to keep track of my levels, of what are the particular levels of this categorical. And then you need to provide these various operations that dtypes need to provide. Like, when you index an array, it finds a chunk of memory, and then it gives you a Python object from it. Dtype has to know how to do that conversion. Or vice versa. When you assign into an array, you've got a Python object that needs to write some bytes into the memory of the array. How does it do that? And then, so you define that interface that you implement, and then you can just say, all right, here's my categorical. It has 3 levels. Here's an array that allows us 3 levels. That's where we want to get to. Next headline feature, duck arrays. So this is sort of a funny name. There's an old sort of, I don't know, joke or something in the Python community that we don't have nominal typing, which is where you say, OK, this function is defined on like only the specific class, like the built-in integer type. Instead, you say, well, this function works on anything that can quack like an integer, right? If it swims like an integer and quacks like an integer, it's close enough. It's probably an integer. Now, and we're talking about specifically at the array level. So NumPy arrays are quite flexible and quite powerful. Like it's a good sort of default way of doing things, but there are also a lot of kinds of other ways you might need to store your data in other cases. So you might need to have sparse data. You might want to have an array that's too big for memory and store it, it's distributed across a cluster in memory, and so on, right? And right now, the problem is the other parts of NumPy only work on ND arrays specifically, not any sort of alternatives. So we want to make it possible for you to define your own classes that implement other kinds of array storage, but make them quack like an array. So that if someone written code for regular NumPy, and then they say, oh, shoot, but now I need to run in a distributed way, they can take that exact same code. All the operations they're calling will work on your new array, and they don't have to rewrite all their code. So it's kind of obvious in that sense. And you can imagine it might sort of look like, OK, I'm defining a new sparse array class. So this __ get item method, that's a Python thing. Like if you make the square bracket indexing work, you implement that method. __ array ufunc, that's a NumPy thing. That's if you call one of those ufuncs like log or sign or add on the array, then it checks for that special method and then says, OK, you figure out how to do the looping and all that stuff that your class needs. I don't know what to do with this, but you do. You can take responsibility. This is something this part we actually shipped a few months ago. But it's just the first piece. There's still a lot of other parts of NumPy that don't go through that. So you can imagine, so like concatenation is another operation that doesn't fit that, and so on and so forth. Yeah? Right. Right. So the question is, like, there's a lot of ways strategies for dealing with sparse arrays, and you might want to like pick one or have the code automatically pick one, and is that part of our goal here? So the answer is like yes and no. So again, like I said, for the dtype stuff, we're not promising we're going to give you an all dancing sparse arrays part of NumPy. We want to make it possible for, if you're an expert on sparse arrays, to write a sparse array library And then the people who who are in your field and it's tuned for their problems can use that. And then over time, maybe we'll learn, okay, like we've got some experience, there's been some evolution in this space. There really is a right solution, and maybe it makes sense to move it into NumPy at that state. But again, the problem, right now, in many ways, sort of the NumPy is kind of a bottleneck on development in the Python ecosystem, right? And so, like I said earlier, what we want to do with this funding in part is to act as a force multiplier on our community. But we also want to act as a force multiplier on the whole Python scientific ecosystem. By saying, so now, if you're an expert at that, you can just do that. You can start writing code, ship it, without having to come to us and have a big argument of the NumPy mailing list and figure out, is it really the right thing for everybody that NumPy is using? That's kind of where we're going with this. Does that make sense? Yeah. All right. So that's the end of what I have to say about specifically what's in the grant, kind of those things. I also wanted to talk about something that's a little more of a research project, something a little more in the future, a little more wacky, but it's interesting, so you get to listen to it. So basically, obviously, we want our libraries to go fast. This is a common problem in scientific computing, right, is we have like big data sets to crunch through and all that. And as we know, one of the limitations of Python is that it's this interpreted language. The standard interpreter, which is called CPython to its friends, is kind of slow. Now, there is sort of a standard kind of solution to this, which is you need a just-in-time compiler, which is, the idea is it takes your high-level Python code and it observes what it's actually doing, and then it generates super efficient machine code for exactly that and makes it much faster. This is making one of these things is this huge amount of work. They're very, very complicated, but there is, some stirrings, kind of Python's kind of reaching the point where the economics and such may make sense for these to start to take off. So in particular, there's Numba, which is a project of Anaconda, formerly known as Continuum, which is, you import Numba, you say, this function here, I need it to be fast. You put a little decorator on it, and it compiles it down to machine code, and it makes it fast. That's all. You don't have to do anything when it works, but often it works. Or there's PyPy, which is a general replacement for the Python interpreter, which historically, it makes regular Python really fast, and it's sort of fallen down on things like NumPy. But then this is dated 2 weeks ago today. They say they're announcing they're now supporting some more and more of the scientific Python stack. That's starting to be a real thing. Yeah? They actually support real NumPy. However, we'll get to the issues with that in a moment. Yeah. So anyway, so just hold that thought for one moment. But and so it's right now, people aren't, these things have very little usage, but when the conditions are right, these things can change very quickly. So this is just looking at how JITs came around, were deployed in JavaScript land, right? There's this decade plus where they're just not used at all, and then suddenly there's this phase change. In a few years, they were everywhere. So this is something I feel like, while this is not something that's immediately important, we need to start thinking about this, right? Be prepared for this transition. And there's this basic problem, which is that on CPython, if you want to go fast, you have to shove as much into C as you can. And if on a JIT system, if you want to go fast, that's exactly the wrong thing. And we spent 23 years running in the wrong direction. So let me explain why is that? What creates this huge discrepancy? I guess so. One thing to be clear on is that mostly what I mean is that for a JIT to go faster than CPython, it can't be working with stuff that's in C. Here's why. So here's just a simple bit of code that's it's just summing up an array by doing a for loop, like the kind of thing, if you can't use vectorized operation, you just need a loop, do some loops, do some computation. And now you could imagine passing in just a regular Python list. And now if you run that under a JIT, it's like, well, I'm a Python interpreter, so I know what lists are and integers are and what range is and all of that. I understand everything here, and I can figure out that while it's written in terms of these high-level objects like Python integers and floats and so on, it's equivalent to a much, much, much simpler thing. I can compile this down in just a few lines of assembly code, and it'll go 100 times faster or whatever, because it understands all that is, and it can make those translations. Now let's take that exact same code, but now we'll pass in a NumPy array. And now the problem is the NumPy array, as much as possible, it exposes these high-level operations. Like you can index it with I, and now what that does is then that calls into some C code that's like implemented a fast indexing code in NumPy, which is what you have to do under CPython. But from the JIT's point of view, it just knows I call this function, it does something. It's a total black box. I don't understand what's going on, which means that for when this code runs under, like, say, PyPy with a NumPy array, it can't go faster than CPython, because all the time it has to make exactly the same set of calls to these black box operations. It can't like see that, oh, actually there's a much simpler way to do it. This doesn't, you can also see this in sort of more classic sort of vectorized code. So something like a plus 2b times log c. If you're on CPython, now each of these individual operations is implemented in C, so it's pretty fast. But it has to be executed as a sequence of these individual operations. Right? So first you have to multiply those together, store that in a temporary array, then take the temporary, add it to A, store that in another temporary array, and so on and so forth, right? So this ends up touching, like if these arrays are a gigabyte each, say, that means you had to touch 10 gigabytes of memory, and you had 2 gigabytes of memory overhead for holding temporary arrays while you were doing the computation. Where if you're sort of clever, if you know what these operations actually are, you could realize, well, actually, I only need to do one loop over all of them simultaneously. I don't need any temporaries at all. And it can go about twice as fast and use a lot less memory, right? But again, that's only the case if the interpreter can look at these and say, oh, actually, it just says 2 times b. Actually, I know that's a loop that's doing these kinds of mathematics. I understand all that, right? So in principle, this is possible, but sort of getting there means you can't be locked up in this black box of C code. And it's not just NumPy that has this problem. So like you can imagine like a pandas operation you want to group by. There's some chunk of arbitrary Python here, and then filter. Now, if you're, from a God's eye view, you can say, like, there's probably a really efficient way to do that. These are really simple functions. We could kind of like inline into the group by code and rearrange things in a clever way. But you can't do that because pandas is written in C as well. It has the same problem. So right now, the only way to sort of get around this is when you write your compiler, your JIT or whatever, you hard code in knowledge of like, okay, well, that's a NumPy indexing. I know how that works. We actually bake it back into the language. And that's sort of one of the directions the PyPy folks have explored. That's what Nell was referring to. But like, you can see this is like obviously, like this is not a sustainable, scalable, practical way to do things, right? I mean, you can't, surely nobody would actually do that seriously. People do that really seriously a lot, actually. So I'm worried, right? Is that this is a tremendous investment to build these things, right? So like, how does Numba work? They have re-implemented a whole, like most of NumPy in their own sort of special way so that when they see a call to NumPy function, they can swap in their implementation instead that their compiler knows how to understand. This is like a huge investment. It's just like not scalable or sustainable, right? If something goes wrong, you get the wrong result, like how do you even know which code you are running? Are you gonna, like someone files a bug report saying, I called this NumPy function, I got this result, but actually they didn't call the NumPy function. It's just what it looks like in their code. The compiler went and called some other function instead. Like what do you do? How do you handle that? How do we respond to that kind of bug report? How do we even know what's going on? There's a problem, like I just told you in the first talk, all these wonderful plans of how we're gonna start changing NumPy. And then if there's all these bug-for-bug re-implementations, how are they going to keep up? How are they going to make sure they're using the right version, right? And that's just for NumPy, right? We want pandas to go fast too, and so on and so forth. So like a good academic, when I get worried, I hold a workshop. So thanks to Intel and SciPy for sponsoring this. I, last year, sort of tried to drag a bunch of compiler authors into the same room to talk about this problem. And what we came up with is that, well, so first of all, like there's some constraints. So here's what we're trying to do, is we need something that, we need to have some way we can write down how NumPy works, like write the code in some way that there's just one NumPy. That's the first rule, right? We can't have like 10 NumPys. That's just never going to work. It needs to be, part of NumPy, not part of the compiler. And a complicated constraint is we can't rewrite all of NumPy at once into some new fancy new language or whatever that the JITs know how to understand. Like we have to be able to move to it incrementally. And whatever we sort of are migrating to, it still has to work on CPython. So that's kind of tricky as well, right? Because that's what everyone's actually using, right? We can't abandon that, even though just, you have to support the future and the past at the same time if you want to get from one to the other. And of course, it needs to be nice, something that these JITs can handle better than they can handle what we have right now. And so here's basically what we came up with. So you can imagine you take some parts of NumPy that are in, this is, remember I mentioned Cython, the mutant hybrid of Python and C? We need something kind of like that, probably not exactly Cython, but for here, Cython is standing in for that kind of thing. So there's some parts of NumPy that are written in this kind of high-level language, high-level, low-level language. And of course, we still will have for a long time parts that are just in C. And this part we all sort of understand is if you have Cython code for the C, you compile it down, you compile the C, you make your shared object. That's how things work now, basically, right? And that's fine. That makes CPython happy. It can call those C black boxes when it needs to. They go as fast as they go. Great. But what we like to also do is define sort of hand-waving calling PyIR. IR here is intermediate representation, which is sort of a term for a way of writing down what code does that's in a format that's convenient to feed into something like a jet. So it's probably not literally the source text, like it's probably pre-parsed and had some optimization done to it and so on. But it's also not all the way down to like machine code. It's still in a somewhat high-level form that your compiler can kind of understand and work with. And so in this language that we're making up, we'll compile it into this intermediate representation we're making up, and we'll shove that in there as well. So you have two copies of the same code in that library. One that's the just black box machine code that runs fast on the processor, and one that's high-level representation that JITs can understand. And then if you're NumPy, for each thing you can pick which one you want to use when they're both available. If this is the only one available, which will be true for, or sorry, like for this kind of case where that's the only thing available for a while, you just have to call it. But hopefully over time we can add more, move more and more stuff into the other side. And then these other kind of compilers can take that. So it's like, you've heard of like a Java virtual machine. We're talking about, we need to build a Cython virtual machine. That's one way to think about it. So this plan is pretty ambitious. There's a lot of details that would need to be worked out. So is it going to work? I don't know. Like it's very expensive, but on the other hand, not doing it is even more expensive, right? There are actually people right now who are like, putting FTEs into like re-implementing NumPy. Maybe they should instead be putting those FTEs into making something that's actually sustainable and scalable, if we can make it work. It's also very ambitious in that this is like, we're talking about this, building this whole new kind of technology, and we wanted for this production and this, like lots of people using it and all that. If I was giving this pitch to industry, they'd say like, so this is another like risk factor. I'm in a university right now, so I can say like, oh, all the better, right? Hooray, we get to do something new. It's research. So that's another kind of thing on the horizon. And that's basically what I've got. I want just to summarize. Hopefully, this sort of gives you a sense both of sort of how NumPy works, and to give you a sense that this isn't just something that fell from the sky. This is like a project. There's real people. There's going to be real people. A lot of interest happening here at Berkeley if you want to get involved. There's going to be lots of discussions about that. And this is not, it's not something that just happened. It's something that's actually, is yours. It belongs to all of us, and that we can all make it better. So that's what I got. Any questions or whatever? Happy to take them now.